Oh, here we go. Welcome back, everybody. So this is section 13.5, the law of sines. Now, big packet of notes. Right? I'm going to try to get this all done today. I checked my video from quarantine last year. It was 44 minutes. So here's hoping. Do it. I think I kind of got long-winded in the video. But whatever I don't get to today, I will finish up tomorrow. That sound good? We're spending 2 days on section 13.5, 1 day on section 13.6, so today and tomorrow. Wednesday, Thursday, section 13.5, Friday, section 13.6, review Monday, look at the board, test Tuesday.
Let's go.
I know, I'm excited too. Test next Tuesday, and that's it. Test next Tuesday, exam review Wednesday, Thursday, Friday, exam for you guys, Tuesday.
Oh, wait, gotcha.
I won't see you on Monday, but then you'll come in and take your exam on Tuesday.
Okay.
All right. So now what we're going to talk about in terms of sines and cosines in these next two sections is how do they apply to things that are not right triangles? Right? We've discussed in a section right triangle trigonometry, and then we talked about, okay, how does it apply, how do these angles of rotation fit in with the sine, the cosine, and the tangent? But now we're going to say, well, what if it's not a right triangle? What if it's something beyond? What if it's a obtuse or an acute triangle? You know, what do we do then? How do we work with sine in that case? Now, the book presents this interesting example for area, and I always like to go over this. This isn't really like part of the curriculum. It's not really a something that you may use very often, but I think it's kind of interesting. A sailmaker is designing a sail that will have the dimensions as shown in the diagram. Based on these dimensions, the sailmaker needs to determine how much fabric they need to have to make the sail. So what am I really calculating here when I want to find the amount of fabric? The height. But I want to find the area of this triangle, right? Because that's going to tell me the amount of fabric I need. But what's missing out of this? The height. And that's a crucial piece of information to be able to solve for area. Because we've learned since second grade, area is equal to 1/2 base times height, right? 1/2 base times height. Am I given the base measure? Yes. Am I given the height? No. So how do we find the area if we don't have the height? Well, maybe there's something else I can calculate. Well, look at the other pieces of information that are given to me. Do you see how the height breaks this big triangle up into two right triangles inside there? So there must be some way that I could use the other pieces, the 73 degrees and this 2.96, to solve for the height. Does anybody see it? Anybody see what I could do to solve for the height? In terms of that angle? Maybe let me ask you this. What's the sine of 73? What's the sine of 73 degrees in this triangle? In this triangle? What's the sine of 73? The opposite over the hypotenuse. So I've created an equation that I can solve for the height. You see that? Just given the angle and one of the other side lengths, I can actually calculate what the height would be. So just running it just as an expression here, the height is going to be equal to 2.96, just multiplying over to the other side. 2.96 times the sine of 73. So if the area is 1/2 base times height, I can say over here, area is equal to 1/2 base times height. And that is a key equation. That's something that is not very often used because you have to have a particular set of information. But that is a really interesting formula in that, take a look at what I'm given. I'm given a side length, an included angle measure, and then another side length of a non-right triangle. And I can find the area of that triangle just given that information. So if you have a side angle side of any triangle, you can actually calculate what the area is going to be. How do I do that? I take 1/2, the two side lengths, times the sine of the included angle. I call that 1/2 AB sine C. Okay, just showing you algebraically, and now it doesn't really matter what this comes out to be. We could run it through the calculator and see, but what's more important to this is that we can create a formula, a generic formula for area given an angle, a side angle side relationship, a side, an included angle, and another side. I think that's really interesting, the fact that we can find the area of a triangle and you don't even have to have the height. You don't have to, as long as you have another side and an included angle measure. So this is the formula that we have. It's 1/2 AB sine C, or 1/2 BC sine A, 1/2 AC sine A. Excuse me. All you really need is two sides and an included angle. You take 1/2 the two sides, multiply the two sides, times the included angle. Now look, they're giving you this diagram that we're going to use pretty often from here on out. If you have a non-right triangle, you can put the capital A across the triangle from the lowercase a, capital C across from lowercase c, capital B across from lowercase b. So capital letter is denoting the point, the angle. Lowercase letter is denoting the side across from it. And I can use this area formula for any piece. So say you had these two side lengths and this angle. That would be 1/2 AC sine B. Say you had these two side lengths and this included angle. 1/2 BC sine A. Say you had these two side lengths and this included angle, that would be 1/2 AB sine C. And that's the formula that I like to use, 1/2 AB sine C. So let's do that. First off, can I actually find the area of this triangle? Do I have the correct pieces of information? Do I have a side angle side relationship? Yeah, I do. I do have a side angle side relationship. I've got the 3 as the side, the 40 as the included angle, and then the 5 as the other side. Yeah, we're on the top of the second page already. A lot of people just kind of sleeping on me. So I'm going to use my area formula. Thank you. I'm going to use my area formula, 1/2 AB sine C. As long as I know I have that side angle side relationship, I can say area is equal to 1/2 side length times sine of the included angle. So let's go and take a look. Let's see, 0.5 times 3 times 5 times sine of 40. 4.8. I'll make sure I'm in degree mode. Yep, I'm in degree mode. So 4.8. 4.8. Does that make sense within the context of the triangle? Yeah. It's not the biggest side. It's not the smallest side. Bigger sides are across from bigger angles, right? It's that hinge theorem you learned last year in geometry. All right. So that's a unique formula that talks about area when you don't have to have the height of the triangle. Okay, area formula when you don't have to have the height of the triangle, 1/2 AB sine C. All right. The next thing I'm going to do is I'm going to kind of break away from the guided notes a little bit. You see the law of sines right in front of you. You might have worked with the law of sines and the law of cosines last year in geometry. Not really sure how far in depth you got with it. But there's something that I want to do with you guys. I want to derive the law of sines. I want to create the law of sines for you guys. So you can see where it comes from. Because again, especially with an honor class, I think it's really important to show you guys where these things come from. So what I'm going to do is I'm going to start out with a generic triangle ABC. And that means my little b is down here, my little a is over here, my little c is over here. Okay. What I'm going to do is break this triangle into two different pieces. I'm going to break this triangle into two different pieces by dropping a height from capital B over to lowercase b. I'm going to create a new piece of information. I'm going to create my height in there. Still making it generic. I'm still saying, okay, this is just arbitrary h, whatever that height turns out to be. So let me ask you this. Actually, I don't even need to use a theta. I'm just going to use the capital letter A. What is the sign of A? What is the sign of capital A? In terms of the little triangle that it was broken up into. What is the sign of A?
H over C.
H over C. Good. You see the small right triangle that I have on the left side, on the inner left side of this triangle? Opposite H over hypotenuse C. Okay, well let me ask you this then. What is sine C?
H over A.
H over A. What's the two things that both of these equations have in common? H, right? Remember the A is the lowercase a, the capital A, the lowercase c, the capital C are not common parts because they're not denoting the same thing. The only piece of information that I have that's similar to both of these equations is H. So maybe I can create some new equation when I solve for H. Like for example, if I multiply C over the other side, I'm going to get C sine A, and I'm going to get A sine C. And what can you do with two equations that are equal to the same thing? You check those two things equal to one another. Right? That's that transitive property. If C sine A is equal to H, and H is equal to A sine C, then C sine A has to equal A sine C. So C sine A has to be equivalent to A sine capital C. And now, a little presto changeo, divide the A over to the left side, divide the C over to the right side, and I get sine A over A is equal to, or do I write it the other way? Hold on one second. No, I'm good. Because you could express this as A over sine A is equal to B over C over sine C. Sine C over C. And that is the law of sines. That is the law of sines. What does the law of sines say? The law of sines says that you could take any A. Now remember what I've got here, capital A to lowercase a, side across from opposite angle, right? You can take any angle and put it over its opposite side. Take the sine of that angle, put it over its opposite side. And you can, and if you have another piece of information, you can take that angle over its opposite side and set them equal. They are proportional to one another. Okay? Every angle in a triangle's sine, the ratio of any sine of an angle over its opposite side is equal to any other angle's sine over its opposite side. And I kind of went through all of that with you guys.
But how would you do the sine of B if it has like two triangles on it?
Well, in that case, what we would do is we would drop a different height in. So instead of when we started here, if we drop a different height in, if we had said this instead, wherever the height would end up there, we could say sine B sine B is equal to H over C. Sine C is equal to H over B. And then have sine B over B is equal to sine C over C. And then we can say...
What if B is obtuse and you can't really do that?
It still works. Just the triangle that you would have would be outside. So like if you're talking about a triangle like this, if you drop a height in there, you'd still have two right triangles. The right triangles would just be here and here. You see that? And you can still find the signs the exact same way. It still works, trust me. Yeah. So moral of the story is this is the law of sines. Sine A over A is equal to sine B over B is equal to sine C over C. Now, it's interesting that you bring up the whole obtuse thing because there is actually an ambiguous case to the law of sines. And we'll talk about this here in a second. When our angle is obtuse, there are weird things that may happen. When the angle is obtuse, there are weird things that can happen. Now, the law of sines allows you to solve a triangle as long as you know either of the following. Now, when I say solve a triangle, I mean find all missing parts. So when the directions say solve this triangle, I'm telling you find all missing parts of this triangle. Now, you have to have either two angles and a side. So we've either got the restriction of having angle, angle, side, or angle, side, angle. Now, I leave space in here so that you see that I can show you what it looks like. Remember, if you've got a triangle that's an angle, angle, side, right? If you've got two angles and a side, you can use the law of sines. Or if you've got angle, side, angle. No matter what their orientation may be, if you've got two angles and a side, you can use the law of sines. Now, if you have two side lengths and the angle measure that is not in between them, you cannot use, well, you can use law of sines, but you have to be very careful. Okay? If you create a bad word, if you create an angle side side, you can use the law of sines, but you just have to be very careful when you use the law of sines. This is that ambiguous case. If the angle is obtuse, something might be weird. Okay? So, let's take a look at this one first. What type of information am I given? Am I given two angles and a side or two sides and an angle? Okay, so there's no ambiguous case. I don't even have to worry about that weird thing that we don't even know what it is yet. I'm given two angles and a side. And what are the directions? Solve the triangle. Okay, so if I want to solve the triangle, that means I'm going to find angle E, I'm going to find side E, and I'm going to find side D. Those are the three missing parts. Now notice that I'm given three parts and I'm looking for three parts. You have to be given three parts of the triangle. Now, what's the easiest piece of information to find? Angle E. Just take 180 minus the other two angles. So I got 180 minus 33 minus 28, and that's going to get me 119 degrees. Okay, so that's 119. Now, at this point, I can use the law of sines to find either of the other two sides right away. So, it looks like I put side E next. Let's find side E. So we would be saying sine of an angle, sine 119 over E, sine of its angle over its opposite side is equal to sine of an angle over its opposite side. Now, what do I want to choose? Do I want to choose F and lowercase f, or do I want to choose D and lowercase d? F, because I don't have D, right? I want to do sine 28. Always go for a set of information that you know. You always want to have just one missing piece out of the four. Now, again, this is a proportion. Let's cross multiply and divide. So this would be 15, and I like to wait until the end to round. So you're going to see me write it out all algebraically. Sine 28, and then we divide over by sine 28. So 15 sine 119 divided by sine 28. That's equal to my E. So 15 sine 119 divided by sine 28, which gets me 27.9. What did it say to round to? Here's 10. 27.9 is good then. All right, 27.9. Now, you know what a lot of people try to do at this point? Pythagorean. Can I use Pythagorean theorem? No, it's not a right triangle. Yeah, don't be tempted to use the Pythagorean theorem. You can't. But what we can do is jump back to, law of sines again. Sine of 33 over D. That's the piece I'm looking for. That's the only piece left over. Sine 33 over D is equal to, and now we can choose to either go with E or F. Let's go back to F because that was a piece of information that was given to us. Sine 28 over F, which is 15. And now we again just cross multiply and divide. 15 sine 33 is equal to D times the sine of 28. So I divide over the sine of 28, I get 15 sine 33 divided by sine of 28. Okay, so 15 sine 33 divided by sine 28. which gets me 17.4. Okay, and there's all of my information that I needed to find. Questions about that?
No.
We good about that?
Yeah.
Okay, so let's talk about this idea of, oh, I still have it prepped. Please tell me this is still going to work. Yeah, let's go. Let's talk about this thing that I call the ambiguous case. Okay, let's talk about this thing that I call the ambiguous case. Now, when you have, and this is, please make note, this is only when you have angle side side. When you're given a bad word, the ambiguous case could come about.
Why don't you go backwards?
What's that?
Why don't you go backwards? That's not bad.
Or a side side angle. You would have to. So an angle side side. When you have two sides in a non-included angle, you're going to have you have the possibility of having an ambiguous case. It doesn't mean that there's always going to be an ambiguous case. You have to check to see if it's there. Okay. Now, what do I mean by that? Now, let me get my mouse here, because I need to man the ship down there. All right. So what I'm going to do is create for myself two set sides on a non-included angle. I have to refamiliarize myself with this a little bit. I want to create an angle with a given size. Let's go 60 degrees. Okay. And then I want to do two set sides. I want to do, let's do it from here. Segment with a given length. From here, let's make it a 5. Oh no, I want it to be on that. Wait, I gotta undo that. No. There's my undo button. What's these things down here? Yeah, I could just delete them. Yeah, right. Okay, I think I need to do, segment with a given length first. I think I needed to make this 5 first. And now I need to go move this up. And now I need to go angle with a given size here, here. Let's go 60 degrees, but now I want to go clockwise down there. I want to make a ray out here because I don't know how long this side is going to be. And then if I put another, yeah, this is going to work here. If I put another segment in here, say this was length 3. So isn't this a, oops, don't create a point. Don't do that. No, cancel. Say, there we go. Say we had this triangle with this given set of circumstances, or the possibility of having a triangle. I was given the side 5, the side 3, and an angle of 60. Could I possibly make a triangle with that information? Oh, that's a marker. Could I make a triangle with that information? Does it reach the other side?
No.
Does it close the triangle? No. So this is case 1. There could be no triangles at all with that given information. There are 3 different possibilities. The first possibility is that there are no triangles at all. What's going to happen algebraically in this case? Well, when you go to do the law of sines, you're going to end up getting inverse sine of a number bigger than 1. What happens when you try to take inverse sine of a number bigger than 1? It's undefined. It's error. The domain of inverse sine is between -1 and +1. So you're going to get an inverse sine, something between smaller than -1 or bigger than +1. Okay? And what that means is you're trying to create this triangle that's never actually going to reach its opposite side based on that information. So let's delete away this point and maybe make that side a little bit longer. What if I make this side, the first side was 5, maybe let's make this side 7. Now, can I create what? A circle. What?
Yay.
What? Can I create? No, I want the move tool. Can I create a triangle here now? Yes. This is the second option. Having just one triangle. I've got a set angle, a set side, and now a third set side. I can create a triangle. And it's good. It meets right there. And then I could use sine B over, sine angle over side is equal to sine angle over side, and go from there and try to find the rest of the piece of information. Okay. Now this could swing, and I could make a triangle over there, but it's really going to be pretty similar. That would be outside the triangle, but that would be inside the triangle. Now, what if I do this? Let's delete away that C, and let's make that something smaller. I've got to strategically pick this now. Segment with a given length. Okay, I did 3 and then I did 7. Maybe I do, stop it. Maybe I do like 5.5. Let's see if that's going to work. Use the move tool. Okay, we have a try. Nope, that's not going to work yet. Let me delete that away. And let's try instead segment with a given length. Let's do 4.5. I know 3 won't work. Oops. Yeah. Okay, I have a triangle there, right? With a given set of information. Our third option is, can't I create another triangle in there? I have 2 possibilities of triangles within this given set of information. I have not only an obtuse triangle, but also an acute triangle. See, this is that whole idea of having an obtuse angle. Look at angle C. Is that obtuse or acute? It's obtuse. Look at this angle C. Is that obtuse or acute? It's acute. So you have the option of having an acute angle C or an obtuse angle C. So there are really 3 different options that you could have with the ambiguous case of the law of sine. You could have no triangles at all. You could have 2 triangles, or you could have 1 triangle. Right? You could have no triangles at all. You could have 2 triangles, or you could have 1 triangle. Okay. Let me show you what this looks like algebraically. Determine the number of triangles that can be formed using the measurements set A is equal to 50, B is equal to 20, and angle A is equal to 28 degrees. So here's how I draw this out. I'm going to start with my angle, 28 degrees. I'm going to draw a ray down here. Here's angle A. And I'm going to generally sketch the angle 28 degrees. This is 28 degrees. Side A is 50 and side B is 20. Now, angle A is 28 degrees. This must be my 50. Right? I can't put 50 here because angle A and side A have to be across one another. And then if I put this side as 20, that means this is capital B, and that means this is capital C, and this is lowercase c. Now, what's the only piece of information that I can find using the law of sines with this given set of information? I already have angle A and side A. What's the only thing that I can find? Angle B, right? Angle B. I've got angle A and side A, and I've got side B. So the only thing that I can find here is angle B. Could I find anything that has C included with it? No, because I'm going to end up having to write sine C over C, which you can't have 2 variables. So I need to write sine 28 over 50 is equal to sine B over 20. Now we cross multiply and divide. 20 sine 28 is equal to 50 sine B. I divide by 50. 20 sine 28 over 50 is equal to sine B. So sine B. How do I solve for B? Inverse sine of the opposite side. So inverse sine of 20 sine 28 over 50. Now, here's how I would recommend you putting this into your calculator. I would take 20 sine 28 divided by 50. I don't know why we're out of parentheses there. And then take inverse sine of that. Inverse sine of that. That's going to be 10.8 degrees. 10.8 degrees. Now, let me ask you this. Obviously, there is a triangle. The option 1 is out the window. I have a triangle. I have an angle B. If there were no triangles, you would have gotten an error right there in your calculator. So we have either 1 or 2 triangles. Since we found a valid angle B, I've got to break this up into 2 cases. I'm going to say case 1, and then I'm going to say case 2. And we have to check for the we know case 1 exists, but now we have to check for the existence of case 2. Case 1, the angle B for case 1 is 10.8 degrees. We just found that. And then we have to find angle C and side C, right? Let's check for the existence of a second angle B. Now, how could there possibly be a different angle B? Well, 1 is the acute measure, where 1 is the obtuse measure. We just saw that within that diagram that we were just working with. What does that mean? We had just gotten inverse sine. When we did this calculation, it was inverse sine of 0.1.
I just realized I got my AP micro test right before our exam today.
Okay.
Can I come in sometime tomorrow?
That's fine.
Okay.
Just do it during your class tomorrow.
Okay, that works.
Just come in a little bit.
Okay, I'll email you something.
Okay. So inverse sine of 0.1877. Now, we just did something like this on our quiz. We found inverse sine of a decimal. Aren't there 2 locations of inverse sine of that 0.188? Or 0.18, yeah, 0.188, I guess. Think about your unit circle. Where is 0.188? Right there, right? Somewhere over here, and also somewhere over here. There are 2 locations with that sine value. 10.8 is one of them. What's the other? What's the other angle that has that sine value? 180 minus 10.8. The supplement of 10.8. So the other option for case 2 of angle B is 169.2. So let's check to see if that actually exists. Let me ask you this. What would angle C be? No pun intended, sorry. What would angle C be if angle B was 169.2?
It wouldn't work because angle.
It's over 180,
Yeah,
right?
over 180.
So I would say 180 minus 169.2 minus 28, right, to find my third angle. You know what that tells me? The fact that this is a negative angle? Case 2 does not exist. When you get an incorrect third angle for case 2, when you get a negative angle for case 2 does not exist. So then you finish with case 1. We finish with case 1. So we take 180 minus 10.8 minus 28. 141.2. I'm going to write this in blue. 141.2. And then we find side C. We were given the angle side pair of 28 and 50, so sine 28 over 50 is equal to sine 141.2 over side C. Going to finish off case 1. We proved case 2 did not exist, so now we finish case 1. Cross multiply 50 sine 141.2 divided by sine 28 that will give us 66.7. And that's my only answer for case 1. There is no case 2. There is no second case. So what did I show here? I showed that there was at least one triangle. How did I do that? I found an initial angle B that showed that there is at least one triangle. Then I have to check case 2. I have to check case 2 by finding the supplement of the angle that I found and seeing if that could also create a triangle. Okay, based on the given information. Angle C did not exist, so therefore I can't work with it. Let's do one more of those. Okay, so this set of information I've got, side A is 14, side B is 20, and angle A is 39 degrees. All right. So we've got angle A is 39 degrees. I'm going to draw myself a little ray. 39 degrees would be something a little less than 45, so there's 39 degrees. Side A is 14. Side B is 20. Capital B, capital C, lowercase c. So let's check to see if at least one case exists. We do so by using the law of sines. Sine B over 20 is equal to sine 39 over 14. We cross multiply and divide. You know what? I'll show the work there. 20 sine 39 is equal to 14 sine B. Divide the 14. 20 sine 39 over 14 is equal to sine B. Sine B. And then I take inverse sine of 20 sine 39 over 14. And that's my B. Let's see if that's valid. 20 sine 39 divided by 14. Is it going to give me a valid angle? Yes, because it's between -1 and +1. It will because it's between -1 and +1. Let's see what it is. Inverse sine of my angle is going to give me 43.8 degrees. 43.8 degrees. So I know at least one triangle exists. If you get an error right there, there are 0 triangles. It's that first option where it's swinging, but it's never going to hit the bottom. So case 1, angle B is 43.8 degrees. Angle C and side C we don't know yet. Let's check for an existence of case 2. Let's see, what would I do to find the other angle B? The obtuse angle B. 180 minus 43.8. Let's do it. $136.2. Okay, again, this is 180 minus angle B. Okay. Let's check to see if angle C would make sense, if angle C would exist in case 2. 180 minus 39 minus 136.2. My initial angle A, 180 minus 39 minus 136.2. Would it exist? Yes. It's small, but it does. 4.8 degrees. So now we finish off case 2 by saying sine 39, go back to our original sine 39 over 14, is equal to sine 4.8 over C. And now we solve that proportion. Cross multiply and divide. 14 sine 4.8 divided by sine 39. 1.86. That's case 2's C value. Because obviously if angle C was really small, then side C would also be really small comparatively to the 20 and the 14. So let's finish off case 1 now. Case 1, I got 180 minus my 43.8 minus my initial angle of 39 degrees, so 97.2 degrees. And now we finish off side C. This side C, case 1's side C, with sine 39 over 14, my initial angle side pair given to me, is equal to sine 97.2 over C. Cross multiply and divide. 14 sine 97.2 divided by sine 39. 22.1. So there exist 2 triangles with that information, and those are the different answers for both triangles. Let's go. 4 minutes to spare. I should stop the video.
You still have your voice.
I still have my voice. Look at that. Look at that. I was at 43 minutes on that other video, 41.